Section 2.6, rational functions. We are now finally going to get into the rational function phase, out of polynomials into the rational functions that form 1 over x to the power of n. So here we have our parent rational function, f of x equals 1 over x. We have these defining traits of them, the asymptotes, vertical, horizontal asymptotes. So this imaginary dotted line here, vertical asymptote, x equals a, because vertical lines have the form x equals. The horizontal asymptote, the line y equals b, because horizontal lines have the form y equals. Now you may have heard in the past asymptotes are these imaginary boundaries or barriers. The function can get infinitely close to them, but they can never touch them or cross over them. It's a pretty good introduction to asymptotes. It's not really what they actually are. Asymptotes are about behavior. For a vertical asymptote, the function, the y values, approach positive or negative infinity as x approaches the a value, x equals a, as we approach a either from the right or left. So it's not about an imaginary boundary you can get closer and closer to but never cross. It's more about behavior. As we get closer and closer to x equals a from the left, the function goes infinitely down from the left. From the right, the function infinitely goes up. And it's the same for horizontals. The function approaches a specific value as x goes infinitely to the right or infinitely to the left. So as our x values go to the left, what y value they're getting closer and closer to? Same here. As we go to the right, what y value are they getting closer and closer to? Now there's a whole lot of ways that rational functions can play out. There's a whole lot of ways the asymptotes can play out. So you have to remember, based upon what you're given, what could happen. So there's really three cases. For the asymptotes. All right? Vertical asymptotes, those are at the zeros of d of x, the denominator of your rational function right here. So whatever's in the denominator, take your denominator, set it equal to 0. So for number 1 here, set denominator equal to 0 and solve. That gets you your vertical asymptotes. The horizontal asymptotes, there are three cases. And it has to do with the degree of the numerator and the degree of the denominator, the largest power in the top and the bottom. There's three ways that can shake out. Either the degree of the numerator is less than the degree of the denominator. Then that means your horizontal asymptotes are automatically the line y equals 0. So for example, you'd have 3 over 2x plus 5. The degree of the numerator is 0 because there's no x term, so it's x to the 0. The degree of the denominator is 1, and 0 is less than 1. The degree of the numerator equals the degree of the denominator. What happens then is that the horizontal asymptote is the ratio of the leading coefficients. The leading coefficient on the top and the leading coefficient on the bottom. So for example, 2x squared minus 3 over 5x squared plus 5. Top and bottom are both a power of 2. So you have a squared on the top, squared on the bottom. So your horizontal asymptote is the ratio of the leading coefficients. It would be 2/5. And then if the numerator is greater than the denominator, there is no horizontal asymptote. So like an x to the 5th over an x to the 4th, or an x to the 3rd, or an x squared. There is no horizontal asymptote. There's a special exception to this, though. So there were 3 cases, but now there's like 3.5. If the n is greater than m by 1, So let's say an x to the third over x squared. That results in what we call a slant asymptote. All right, so now you have a diagonal line that acts as an asymptote. How you find that is you take your numerator, you divide it by your denominator, and discard any remainder. So thinking about your polynomial division, the answer you get up on top, y equals that, that's your slant asymptote. Get rid of any remainder, you don't have to worry about it. So to look at a couple of these examples in action, okay? Just kind of identifying some horizontal, vertical asymptotes, some zeros, all that good stuff. We're going to find the zeros for these also. So find all vertical and horizontal asymptotes. So vertical asymptotes. This is the same every time. Take your denominator, set it equal to 0, and solve. So x squared equals 1, square root, plus minus 1. There you go. Horizontal asymptotes. Now n is equal to m. We have squared over squared. So that means we're going to have a ratio of the leading coefficients. So we have a leading coefficient on the top of 2. We have a leading coefficient on the bottom of 1. We get a horizontal asymptote of 1. To find the zeros, take your numerator. Think about when a fraction equals 0. Think about fractions that equal 0. Okay, 0 over 2, 0 over 3, 0 over 5. All right, the numerator is equal to 0. So 2x squared equals 0. Go ahead and solve, and you get x equals 0. All right? So vertical asymptotes, set your vertical asymptotes, set your denominator equal to 0. Horizontal asymptotes, look at the degree of top and bottom, compare them. Zeros, set your numerator equal to 0. Over here. Now I think we have quadratics. I think it's going to be a good idea to go ahead and factor these down right off the bat. Because a lot of times we're looking at factors, we're setting things equal to 0. So let's factor the top, x squared plus x minus 2, that is x plus 2 and x minus 1. Down here we're going to have x minus 3 and x plus 2. Now look at what happened, okay? We have a common factor in the top and bottom. That's going to affect some of our work later on, okay? Now vertical asymptotes, set the denominator equal to 0, okay? Now, when you go to solve this, you'll see that either x minus 3 equals 0 or x plus 2 equals 0. But when you think about the zeros, you want to set the numerator equal to 0 and solve. Now you see this common factor, x plus 2. It's in the numerator and the denominator. So here, x plus 2, you get x minus 2, and x minus 2 would be a vertical asymptote. But here, it would be a 0 crossing the x-axis. Well, how could you cross the x-axis and have a vertical asymptote at the same time? That's not possible, all right? So this repeated factor ends up not affecting either the vertical asymptote or the 0. What it actually turns out to be is it turns out to be a hole in the graph. It's a unique, discrete point that does not exist on the graph. Looking at the graph, like on a calculator, you wouldn't even see it. It would just trace right through it. But recognizing a common factor as a removable discontinuity that results as a hole in the graph, it does not factor into the zeros or the vertical asymptotes at all. So a vertical asymptote at x equals 3, a 0 at x equals 1. Horizontal asymptote, same thing happened again. N equals m, therefore y equals 1 over 1, which is just 1. So, a little bit of practice with vertical, horizontal asymptotes and zeros, looking at this kind of unique situation where you get a repeated factor in the top and bottom, resulting in a removable discontinuity. That value doesn't factor into either the vertical asymptotes or the zeros. So there are 2 more examples down at the bottom of the page, creating the graphs, finding all this good stuff. Check those out, and then check the answers in my completed notes online.